Good catch, thank you. Okay, apologize for everybody. I'll limit my interaction on this whiteboard and this. Questions about anything, you think? Solutions that you are curious about, I think. Okay. Nobody. Can you hear me? I mean, the computer behaves very strange today, and I cannot convince it to recognize that there are more cameras in the room. So we'll do our best with on one of them. So if there are no questions about anything, that is so quiet, let's discuss a few more connections between Voronoi diagrams. And lower envelope, another way to move from 1D to 2D and then from 2D to 3D. And along the way, we study a lot about what this Voronoi diagram looks like. So I want to tell you what is a lower envelope of a set of functions is. What is the lower envelope of a set of functions? And actually, we have seen lower envelopes already, but you're going to see them once again. You just didn't know that's how it's called. So I have a set of functions. Sometimes they are linear, sometimes not, I don't care. I have a set of functions, and now formally, in a way that is, of course, completely accurate and tells you very little intuition about what's really happening, is that I am looking for all the points in the, now it will be the plane, it will be the Z and X, it might be 3 dimensions. You'll see in a second why I prefer to use Z rather than Y. So I have a set of functions Z equals F, let's call this guy, F1 of X, and this guy will be F2 of X, F3 of X, F4 of X, and the lower envelope, sometimes you'll hear it called the minimization diagram. If that's the only working camera, I need to try at least not to occlude it. Minimization diagram. That I will be standing right here at this particular point, and I will gaze into the sky, look into the sky, look vertically just above me, shooting a ray vertically up, and as I'm shooting this ray vertically up, I wonder what is the first function that I meet. And in this case, it's F1. That likes the lowest envelope out of all these functions. Of course, it could be that this function is not unique, so essentially I want to say a point is on the lower envelope. A point is on the lower envelope if there is no functions that are above it. Maybe there are some other, if there are no functions below it. So this point is on the lower envelope. This function is on the lower envelope. There is nobody below them. There are a few functions above them. There might be other functions just as low as these functions. But that, of course, is the lower envelope. And I don't insist on standing right here. I can move along this line. And for each point, I will see who is the lowest function at this part. And for a while, if it's linear function, then for a while I will be on F1 until I'll move into a segment of F2, then I'll move into F3, F4, and so on. And have you seen such lower envelope, where did we play with this?
Linear programming.
Linear programming. It's essentially, if I say all these half planes, each line defines a half plane, that's always. Some of these half planes contains minus infinity, like looking downward. Some of the half planes contains plus infinity, looking upward. Here are all the half planes that contains minus infinity, like looking downward, and the lower envelope is nothing but the boundary of the feasible region. In the linear programming, we also had several functions that were going and pointing upward, but I don't want to speak about them right now. And of course, you know how to compute this lower envelope if it's linear functions, if it's half planes. Then we talked about divide and conquer. I'll show you more tricks. We will see that it's actually very much related to convex, to computing convex hull, and so on. So we'll go back to computing lower envelope of linear functions again, but what I really want to give you right now is more insights about what's happening in 3D. And how is this all related to Voronoi diagram. So what you see over here are 4 points, namely A, B, C, and D. Since this screen is captured more or less okay, I'll use the other side of the screen to tell you, and it's not in Zoom. I'm going down into my points are now on 1 dimension. Just for visualization. All my points lives in 1 dimension. This will be P1, and it has some X value. Doesn't have Y, and again, I'm using Z as the height. Let's use it also as a camera, in case I'll accidentally say something important. Here's one of my points. P1 in the GeoGebra, I'll call it A, and I want to define a function which would be f1 of x would be the distance from x to P1, or to A. Not too hard. For every point in the plane, I measure the distance to P1, and what this function looks like, it's just as long as I'm in 1D, I don't need the gymnastics that I'm going to show you. As long as I'm in 1D, this function is, as I'm walking toward P1, my distance to P1 decreases linearly, obviously. This is 45 degrees. And I hit P1 where my distance is 0, and then surprise, surprise, the distance go up. So how to see where is the font, but there is a red point, and that's the cone that it defines for P1. Let's have another point. Here's another point, B. And notice that it's the same angle. It's the same 45 degrees. Right? It's important. There is something called multiplicative weighted Voronoi diagram. It's more important for me to get to this hospital rather than that hospital, so every mile has more effect. So these cones might actually reflect in the angle how much importance or weight I'm giving to a place, but not now. I will not mind additive weight on the other hand, and it will be combined very nicely. Anyhow, as long as everybody agrees that all these cones have the same angle, now I'll ask you, if I'm just standing right here, how do I know out of these 4 points which one is the closest? Now when we know what is a lower envelope, then let's create a lower envelope. I should have described this sentence a bit differently, but that's fine. Let's describe the lower envelope of these functions. It's not a linear function, it's a piecewise linear, but let's describe the lower envelope, all the points that are below everything. Years ago, I described everything that is below. By the way, when I described the lower envelope, I said I'm standing somewhere and looking upward, but somewhere might be in the basement somewhere, very low. I'm below, my viewpoint is below all the functions. But I'm not committing that all my functions will always be above the x-axis. They don't have to be positive. Okay, now what will be my Voronoi diagram of these 2 points in one dimension? It will just mean if I'm standing right here and looking up and asking which function defines my lower, the lower envelope. That is, if I keep shooting upward, this vertical line sometimes meets the function from P1. Sometimes it would meet the function from P2. If there are more PIs, this line might meet them. But what I'm asking is, who is the first function that I meet, going from infinity upward? Which is the first function, the lowermost function, where I'm standing? And where the lower part, the lowermost, of course, might change. Here you see that as I'm moving toward P1, then P1 is the closest. How do I know? Because the function f of 1 is the lowest. It's smaller than the similar function that point B defines. There. But of course, as I'm hitting, this is what? It is in 1D, it's nothing but a vertex of the Voronoi diagram over here. Here I'm just equally distant from A and B. Moving more to the right, shooting upward will meet a segment of B. So B becomes closer. So once again, shooting upward, I'm just asking who is the first graph, the graph of the first, who is the first graph that I meet as I'm shooting my way upward for each point? And the Voronoi diagram just answers you are in different cells according to the 4 points that you see over here. This part that I'm not sure why it is so blurry. It was not so bad last time we played. But this part, as we are moving, you see that I'm moving a vertical line. Remember this vertical line, barely seen as I'm moving. And at each moment, I'm just asking which of all these lines will be the first one that I meet. What is the lowermost one? Talking about it, I can also ask what is the last line that I meet? What is the last function that I meet? Just by the way, I can define what is the highermost function that I meet, which is not the lower envelope, it's the upper envelope, obviously. It's what I see when I'm standing on the roof and looking downward, shooting away downward, and the first one that I meet from the other direction. What is this corresponding to?
Furthest point on
the furthest point Voronoi diagram. But see that the furthest point Voronoi diagram that you have in the homework is exactly, if the points are on the line, you see that no matter what I do, it will only have 2 segments. Well, 2 segments only. There are only 2 points. Not surprising, the leftmost and the rightmost that matters. Anyhow, all this discussion makes any sense or leads anywhere if we'll talk about what happened in 3D. So in 3D, what's the cone that A defined? What this cone corresponds to? Just at least for the people in the class. Let's try to see. Slightly better. What will happen in 3D? You see there are a few points out there. What is the distance function? It's still a cone, but now this cone is symmetric around the point. Everybody agrees? Actually, it took not exactly the distance, but 3 times the distance just for visualization. But now my function is f1 of xy is the distance, which is what? X minus x of a square plus y minus y of a square, all of this to the square root, because I need the distance. And this defines these cones. Right? This cone is nothing but the distance function, but now my distance to a point I live on the xy planes. I'm only moving on the xy planes. I'm looking up, and I want to see which function do I hit the most. Which of these cones is closest to me if I'm just shooting a ray up. Exactly the equivalent of shooting the ray up on the cone in 1D. Now my cones lives in 3D. The apex are just the points, and the distance function that you see over here are just what for every point xy, how far it is from A, that would be one cone, how far I am from B, how much I am from C, how much I am from D. And how do I know which one is the closest? Is the first cone if I'm standing on some point xy, and I'm asking what is smaller, f, let's call it fa of xy, or fb of xy, which would be exactly the same, except that now I'm writing x of b and y of b instead of x of a. However, I want to know what is which one is closer to me. It's the one for which this cone is lower if I shoot away water. And now here in this example, the points happens to be on a line, but it's not really important, but you do understand what's happening right here. Okay, and now to get some better insights about what's happening with all these cones, I need two tricks. Here my function, the distance function, something is, let's use a very deep theorem that would say, let's say that I have two numbers, alpha and beta, and both of them are positive. Good for the camera. Alpha and beta are two numbers that are both positive. And let's say that alpha, both of them are positive. And let's say that alpha is smaller than beta. So that's true if and only if alpha square is smaller than beta square. If one thing is smaller than the other, x squared is behaving monotonically. If you are increasing x, then x squared also increases. So if I have a few functions that are competing with each other, and I'm asking which one is the closest to me, which one is the lowermost function, or which one is the lowermost function, if I take the square of this cone rather than the cone itself, nothing changes. The value will change. The value where my ray hits a number will not be the distance, but will be the distance squared. But the one that is the lowest, the one that corresponds to a point that is the closest, that one will not change. So I still don't understand why I want to do it, but at least square root sucks. They are not stable. Absolute value sucks. It's not hard to compute the derivative at this point. Let's instead take this number, fa of xy squared plus y minus ya squared, take the square root of it, and take the square of this number, which is nothing but kill this half over here. So I'm left with x minus xa squared plus y minus ya squared. And the whole thing is replaced by, now it's not the distance, but the distance square. So now I have, instead of squares, parabolas. Everybody agrees? I just replaced it with a parabola. What will happen if I hit Control T? I'm going to be very sorry. No effect. I cannot increase it in real time. Again, I took the functions. I took the red function at which I computed the exact distance, and instead I replace it by square of the distance. But if at some point red is below the green, then the square of the red is below the square of the green. So the first function that I hit out of all these parabolas, the first parabola that I hit when I shoot a ray upward, that is the lower envelope of these parabolas, is exactly the Voronoi diagram. You know who is your nearest neighbor based on the first rays that you hit. So parabolas are a bit more friendly, but to make them even, let's see them in 3D. So now instead of cones, I have a paraboloid. Just a cone, this parabola, now it's central symmetric. Okay, so I can turn, this is, instead of cones, I take the square, and these are paraboloids. And it still doesn't see as it's leading anywhere, but at least I don't, correctness-wise, if it's the lower envelope of one is the same lower envelope of the other. The minimum function is still the minimum when I do the square. Okay, now I need another trick to tell you something interesting. So now let's think about it a bit more carefully. Fa of any point x, y was x minus xa squared. I'll write it once again. X minus x of a squared plus y minus y of a. The a is one of the points, squared. That's my distance function, squared to the point A. Right? From the point xy to the point A, this is a distance squared. So,
could you explain again why we take the distance squared?
So I can use the second trick that is coming up.
Oh, okay.
Now I'm doing a trick that by now people in machine learning are using quite frequently, made up to a lot of other domains. And I don't know where it started from. Let me write it a bit more explicitly. This is what? This equals to x a squared plus y of a squared minus 2x a minus 2y of a plus x squared plus y squared. Surprisingly, no mistake so far. So if everybody agrees that this is just an interpretation of this, that this is just this, then notice what's happening here. This is a constant that depends only on A. This is something linear that depends both on A and on x, y, but it's linear on x and y. And this is the x squared and y squared that give it such a nice shape. But now let's compare it to fb of xy, which is the same x of b squared plus x or plus. You don't need to write it, y of y squared of b minus 2xxb minus 2yy plus the same x squared plus y squared. And what I want to draw your attention is that the nonlinear part, is the same for both A and B. The linear part here depends on where A and B are in the plane. But the nonlinear part is the same for the both functions. Now, when I'm taking my point Q and ask who is the highermost point, of course, if I take some value and subtract the same value from both functions, from FA and from FB, and ask which one is lower, as long as it's the same value that I subtract from both of them, where I'm standing, I don't change the order. I don't change who is the function above me. So I don't need the cones anymore. But from this moment, I can subtract the x squared from both the A and B, and I'll get a different lower envelope. It will be different functions, of course. What I'll get, but the function for every xy that is fixed, every x only that is fixed, if I'm looking above me, the color of the function above me should not change. If it was determined by A, it will still be A, because I'm going to reduce the same value, to subtract the same value from all 4 functions in this case. So I'm generating a new function. This thing minus x squared plus y squared. And this thing minus x squared plus y squared. And what happens to it? Which function are we getting when we cancel the x squared and the y squared? When we are canceling the x squared and the y squared, looks a bit messy, but it just becomes, for these functions, I just, of course, subtract only the x squared. Well, y is 0, so I only subtracted from each one of the parabolas. From each one of the parabolas, I subtracted x squared. It's different for different x's. Of course, the x squared is different, but when I'm asking which one, but for the same x, I subtract the same value from all the functions. So the order between them did not change. But now I'm just left with a set of lines. And what is a Voronoi diagram? It just to ask what is the lower envelope of these lines. That's what happened if my point lives in 1D. And if my point lives in 2D, and I'm doing the same linearization trick, then I'm left with a set of planes. They don't have to look that nicely. They don't, of course, in general, if here I use the same points where y was 0 for all of them, but in general, what are you getting? You're getting the lower envelope of a set of planes. And that has a lot of nice properties. Like every plane contributes only one cell. And it can be much more general than different distance function. It will still be just planes. As long as they are just planes, intersection of planes looks like intersection of half spaces, sorry. The lower envelope of planes is just a convex shape that looks just like this. Every point, each one of the points contributed one plane, and this plane is just flowing above you. And out of all these planes, shoot up. Voila, the first plane that you are hitting when you are shooting up is the one that determines the closest point. You also see clearly what is the furthest Voronoi diagram. But the order didn't change, so it's just the upper envelope of all these lines. But you see that the computed Voronoi diagram is just like computing intersection of half planes. in 3D, have spaces in 3D. Complete intersection, and what a vertex of the lower envelope is determined by two lines, if my point is in 1D. It's determined by 3 planes. Determined by 3 planes, that's a vertex, which is what? It's the center of an empty circle that can go up. Okay, think about it back, project it back to the plane. What is this? It's a vertex of the Voronoi diagram. Vertex of the Voronoi diagram, if you stand on the vertex of the Voronoi diagram, I'm standing on the vertex of the Voronoi diagram, going a circle around me until I hit one of the points, then it means that I hit 3 points at the very same moment. Yeah, and now it's much easier to compute. I don't have squares, I don't have to compute square roots. And it which that works in higher dimensions as well. So people in machine learning like similar tricks because it moves us from Euclidean distance that involved squares and square roots into support vector machines where I'm looking for plane that separates between one set to another, and I can use linear programming. I don't need to look for fancy functions. Okay, it's much easier to do clustering. Distances of what my measurement is, I can ask who is the nearest neighbor in a much clearer way. The slides are partially prepared for it, so that it was mentioning it before leaving lower envelope completely. Yeah, I'll finish the slides, but hopefully it was clear. People, questions, Zoom or live? About this. Everybody understood how I moved from lower envelope of cones to lower envelope of parabolas to lower envelope of planes. And there is many properties that are obvious when it's lower envelope of planes or lines, like what is the complexity, how many vertices could I have, where every plane only contributes one piece into the lower envelope. In 3D, it will be one connected face that is a Voronoi cell. So sure, the lower envelope will be just, the complexity will be linear. Why? Because it's a planar graph. It has linear number of faces. We know that if everything planar means it's a map. It has edges, faces, vertices. And if one of them is linear, then the other two are linear as well. Everybody submitted homework 3, by the way, by now? I think so, yeah. Any problems about, I was struggling with finding a phrasing of the 6 color theorem, that you can paint every map using 6 colors. Well, you can do it with 4, but you can, if you have the map of the United States, you can paint the map of the United States using 6 colors, so that if 2 states share the border, they have different colors. So you had it as one of the questions, except that I was trying my best to hide that it's just over it, because the proof of this, the paintability of maps is all over the web. Instead, what I asked you was paint the vertices of a planar graph using 6 colors, so that if you have an edge, if you have in the planar graph an edge that connects 2 vertices, they should have different colors out of the 6. And remember what was the algorithm? It was both the proof and the algorithm. This graph that I was talking about is nothing but the dual of the map of, say, United States. Every vertex becomes a state, and 2 states that share the border and got an edge to connect it. And now I want to paint it. And what was the proof that 6 colors are enough? We said in a planar graph, the average degree is 6, and it's actually by just barely minimum smaller than 6, which means that there must be a vertex V that is connected to no more than 1, 2, 3, 4, 5, many neighbors. In every planar graph, you'll find a vertex V that is connected to no more than 5 neighbors. Because if they were all connected to 6 or more neighbors, then the average degree would be larger than 6. So there is such a vertex. Why are we happy about it? Because we don't decide, we postpone as much as possible what is the degree of this vertex. Oh, sorry, I will postpone as much as possible my decision about the color of V. I will not determine its color now. Instead, I will erase it from the graph. I'll remove it from the graph. And now in the resulting graph, I have, it's still planar. By deleting edges, you are not making the planar thing non-planar. So there is still a vertex of degree 5 or less. Remove this one, remove this one, remove this one. Completely analogous to what we did with ears in polygons. At the end, you're left with something that contains, say, less than 5 vertices, which you can paint in any way you want. Give it your 5, use 5 or colors. So let's say that I am just about to put V back. Remember that V was the last vertex, V was the first vertex that I removed, meaning that it's the last vertex that I'm putting back. The degree of V is 5. It's connected to 5 neighbors. These guys already have a color. Green, blue, yellow, whatever you want, maybe green again, I have no idea. But whatever their colors are, brown, magenta, when I'm putting V again, since it only have 5 neighbors, I can always use a 6 color to paint V and not getting any violation. So that was the algorithm that used planarity to use 6 colors. It's a hard question maybe by itself, but you've seen something extremely similar when we did ear clipping of polygons. We said there is an ear in every polygon. Remove this ear from the polygon. It's also a good review for the midterm. Remove this ear from the polygon, paint the remaining vertices. I'll remind you what I'm talking about. There is an ear, namely in the triangulation, there is a vertex V of the polygon that is connected to only other 2 vertices. And in the polygon, in the art gallery theorem, I was trying to paint all the vertices using no more than 3 colors. So the idea was that you removed V, paint everything else. Now look, put V back again. This guy was green. This guy was red. I have the 3rd color to connect to V, and I don't create any disasters because V is connected only to 2 vertices. Okay, so that was slightly tricky. Okay, let's move to QuadTrees finally. I'll show you some materials that I also show in 445 and in graphics, because QuadTrees are so unbelievably useful, but I'll also show you other things that are relevant to application of QuadTrees for more applications. We will talk about balanced QuadTrees and compressed QuadTrees. They are different things, don't confuse. Okay, so switching to QuadTrees, just take care of OBS that is unhappy again. Camera still don't want to speak to us. So, QuadTrees. We are doing two things at the same time now. We are talking about data structures that can help us handle very large amount of data, either for graphics applications, or robotics, or game design, or geographic information systems. And one of the many phases will also help us do generate good triangulations, but for objects that are not just a point or just a polygon. But let's start with QuadTree in general, and I'm creating with a very toy problem, which is I have an image in my image mysteriously. It's it's bichromatic image. I just have two colors, black and white, or because I wanted to conveniently using whiteboard with this green and red, but there is no gray level. Every pixel is either red or blue. And I want to build a QuadTree for it so that I can do various types of operations. And what are various types of operations? I will see various types of queries, like given a query point Q, I just landed at a point. Did I land on a green pixel, or did I land on a red pixel? Or more interestingly, given a query region like a disk, is this disk fully green, or is this disk fully red, or does it have both? Or how much green there is in this query disk? How many green points, how many green pixels, how many red pixels there are? And there will be plenty of other types of queries. And in the book, you'll find a lot of data structures that are very good in solving a particular type of queries. You'll find a lot of data structures that are very good in solving a particular type of queries. But it's not very practical, because usually we don't have one particular type of queries in mind. We want a data structure that will solve any type of queries that we might have about our data, and we'll do all of them decently. It might not be the optimum for any of them, at least not the naive version that we'll start with, but it will do all of them very efficiently. There is a reason that commercially it's very intensively used. Like, I like to tell the story. The grandparent of QuadTrees is Hanan Samet, professor at Maryland, and he's saying, yeah, maybe the theory is not always strong about QuadTrees, but UPS uses them as their main data structure to design transportations, and if such a huge company thought that that's the best data structure / database, they know what they're doing. Okay. So a few assumptions. When I talk, it will be different when I talk about input points. But right now I assume that if there are pixels, then it will be convenient to say there is some minimum granularity, which is single pixel right now. I move away from it when I talk about points. And the whole world has some number, 2 to the age will be the width, 2 to the age for some integer age will be the width. So for example, 1024 times 1024. Right? That would be the size of my world. It will be convenient to think about that the width and the height are power of 2, integer power of 2. Okay. Now, a QuadTree will have the property that every node, like lots of other hierarchical data structures that we'll see, every node has a range. I call this range R of V. In the book, it is sigma of V. It's the same thing. Sigma of V is just in my slide, R of V. The region that the node V corresponds to. And the region that the root corresponds to will be the whole scene. That's its kingdoms, that's what the root is looking at. And in a quad tree, every node either has 0 children, making it a leaf, or it has 4 children. It's not binary tree. Like it's easy to make to make it into binary tree by saying I'll split the 4 into 2. But by definition, every node has either 0 or 4 children. So, who are the children of the root? One of them will be the northwest side of the root. One will be the northeast side of the root, the southwest, and the southeast. So, the root has the region of interest, say everything in the United States. I had a friend that said that she had to leave the United States to see maps where the United States was not in the middle. And so now we talk about the United States and the root. This is a region of where we are designing, say, where to put Walmart. So it will be some geographic application. The smallest region that RV can covered in this 2 example is a pixel, if needed. Okay. And so once again, every child corresponds to one of the quadrants that we're splitting. And in quad tree, if we are splitting a region, it will be into 4 quadrants, and the area of each quadrant is the same. There is a different but similar data structure that we discussed named KD trees, where I'll split the image so that somehow the amount of data from my left and to my right are equal. It's not quad trees. Related but not identical to KD trees. Okay, now to other binary space partition that the book discussed. And sometimes we'll call them the children 0, children 1, 2, 3. And that's convenient. Why? Because when we implement it as a data structure, then every node will be an array of 4 many pointers to possibly other nodes or to null. So it's convenient to know that the first cell is always referring to the northwest quadrant. Okay, back to our image. Every time that I'll talk about quad trees, I'll tell you what is the splitting policy that I'm using to construct this quad tree. So every time that I'm talking about quad tree, I need to tell you what is the splitting policy. In the image part, I'll tell you that every bichromatic node needs to be split. Every node that is completely covering only red pixel or only green pixels, I can leave it as a leaf. So look at the root, look at the whole image, contains both green and red, so it needs to be split. Splitting will be, as we said, always in the middle. And because it's a power of 2, there are no fractions when I break it into 2 halves. It's half on the x, half on the y. And I repeat the same question recursively. Hey, northwest, are you fully green? Yes. So no reasons to further split the northwest node. It stays as a leaf. And this leaf just needs to know that it is fully green. And I don't see any reasons to further split this leaf. And I will not do any rotations later on. Quad trees, I do not do any rotations. I'm very happy with the quad tree being completely unbalanced. Let's continue. Southeast quadrant, fully green. Yes, leave it as a leaf. Yeah.
What's the shape S? Shape S.
That if the input will be a shape, in this case it will be an image, in a few slides it will become points, in a few slides it will become triangles. So it's the quadtree for this C. It's S for C.
It consists of some region of the whole.
Yes, absolutely. Good point. So to start with, S is a whole image, but here it is a recursive part. Then what do I do? So let's see. So I called the construct quadtree. Actually, you can construct it from the bottom up. You can construct it from the root down. Each approach has its own pros and cons. Here I construct it from the root down, and the shape that I'm starting with is a whole region altogether. Asking the root, is the whole shape is fully green in R of the root, or is it fully red in R of the root? Then leave V as a leaf, no reasons to split it, just make it know what is its color, its uniform is around this shape. Otherwise, divide R of V into 4 equal size regions, like for S by itself. We split it into these 4 quadrants, and V itself now will be the happy parent of 4 children. And what are these children? How do I build them? I build them recursively by looking at what do I need to do here? The northeast part, quadrant 1, this is not 10. It's 1 followed by 0, and 1 followed by 2 followed by 2. So the quadrant 1, the northeast, is neither S for this quadrant is neither fully red or fully green. So I'll have to split it as well into 4 quadrants by themselves. So this point V will be the happy parent of 4 children, and I'll repeat it recursively for each one of the 4 children for the northwest of the northwest of the northeast quadrant, quadrant 1, 0. This is this one, no reasons to further split it because it's fully red. Same for 1, 1. Same for 1, 0, fully red, and only 1, 2 needs to be further split because it's neither fully red or fully green. So again, split it into 4 quadrants correspond to these 4 children, and that's it. And you see, this is the whole construction. Again, no reasons to balance. Very, very easy to implement, which makes it also very fast, because very few ifs and special condition. You can actually use it all in one big array instead of using dynamic memory allocation. So it takes much less memory, and you don't really have to have pointers, various tricks over there. How do I do point location? So let's define what is point location. Giving a query point, I give you the coordinates of the query point, and here and many other opportunities in this course, we'll talk about, here's a problem that you can take the data, meditate on the data, and prepare an appropriate data structure so that now we can answer queries fast. Why? Because it's not a single query. If it's a single query, a single time I need to answer it, then of course I can just check all the pixels and find all these queries. I don't need the data structure. The idea is that after you meditate on the data structure, there are lots and lots of streams of data that influence your decisions later, and each one of these queries you want to answer quickly. That's what justifies why you want to meditate and spend more time preparing the data structure. And we already saw some examples about the triangulation, like the Linearization triangulation has a data structure that enables you to find for a query point at which triangle it lies and do it in logarithmic time. That is, you don't need to exhaustively scan each and every triangle to find which one contains a query point. What about here? Much simpler. I have my query point. What do I do? Tap. How do I answer a query? I give you xy. I want to know if the point xy is red or green, given that the tree is already constructed.
Search which leaf node and point is in.
Pretty much. But I'll start from the root.
Yeah.
If my query point is not in the region that the root covered, that usually the root itself doesn't need to know, somebody else needs to know what is this region, but if it's not outside the region of the root, somewhere here outside the image, then we don't answer. Otherwise, what do we check next for the root? You said it, let's say somebody else said it again, saying it again.
Which quadrant it is in?
Before that.
Or, I'm not sure.
My first check is I'm looking for the root and asking, hey root, are you a leaf? Well, that's, if the root is it's perfectly fine that the root is a leaf. And we are just returning the color of the leaf. And that's how it continues. If the root is not a leaf, then I'm checking if it's in which one of the quadrants it is. And there is a nice trick that I've shown in class that essentially says there is, when I'm looking at x, all I need is to pull one bit from x and to say it's 0 or 1. And if it's 0, then it's on the left subtree. If it's 1, it's on the right subtree. And similarly for the y, so it's very easy to know in which of the 4 children I need to check next. Go to this node that contains the query and repeat the same question. Is this a leaf? If not, then in which one of the subgroup quadrants, etc. And because it's a power of 2, the size of the grid, then usually, let's take an example. So for conveniently, I'm saying that it's grid of 1 to the 2 to the h. It's actually 0 to the 2 to the h minus 1, making it that the quadtree will be on the numbers 1 to all the way to 7. And if I have the root of the quadtree, the root, which we'll call, has R of V, which are all the numbers 0 to 7. Go to the left subtree. The left subtree, U, R of U, are the numbers 0 to 3. There are 4 numbers over here. 0 to 3 would be what the left subtree covers. It's a one-dimensional quadtree, of course. And W, R of W, would be the numbers 4, 5, 6, 7. And I continue recursively. So there is no pixel here at the middle. There is nothing that is on the boundary. They're all integers. What's the maximum height of the quadtree? Not hard. Where do you see a letter on the slide that describes the height, the maximum height of the quadtree? H. But I start when the size is 2 to the h. I go one level down. This is 2 to the h minus 1. It's a bit confusing. I don't divide it by 4. I divide the x value by 2 and the y value by 2. So the size of the quadrant is 2 to the h minus 1 times 2 to the h minus 1. And what's the maximum height? If I stop when it is a pixel, then the maximum height would be, of course, h, maybe h minus 1. Okay, but the question about height is in many cases irrelevant because look at this tree. It's not balanced, but it also means that many of my queries, if my queries are distributed uniformly, for many of my queries, I can answer the moment very close to the root. I don't need to go all the way down. Most of the information here is very close to the root. Most of my searches are much faster than the total height of the tree. So it's different than standard QuadTrees. There is a reason that it works so well in practice. Okay, so point location takes order of age time. At most, that's a pessimistic upper bound. And let's talk about QuadTree for a set of points. Now I don't have an image, now I have a set of points. And again, the idea is to make it so that multiple types of queries I can answer quickly. So I need to tell you what my splitting policy is. The splitting policy that I want is that every leaf will contain a small amount of information. Say no more than 17 points inside a leaf. Here it's a bit hard to show in the slide, so I will pick a simpler splitting policy. I'll say if a node contains 2 or more data points, don't get confused. These are the data points, should I say. A, B, C, D, E are data points, let's say, octagons that you see over there. And every other pixel is not a data point. I don't need to store it. Splitting policy in this example, every node must contain at most one data point. At most one data point. So S in this case, to answer your question, S in this case are the data points A, B, C, D, E, and I will assume that they are all in the range of no more than X, no more than Y. I don't particularly care if they are integers or not, so the arguments about the height might be a bit more subtle. But let's see what do I do. I'm asking, hey, the root asks, hey, is in R of V, R of V is still the same, the whole region. R of the root is the whole region. Is in R of V, I have 1 or 0 data point. Now you have 5 of them, A, B, C, D, E, so you need to split. Splitting is still exactly in the middle, no matter how many data points I have in each quadrant. So I still have the 4 quadrants, the 4 immediate children of the root. And I noticed that when I call myself recursively, that in quadrant 2, southwest, there is no data points. So quadrant 2 is left as a leaf, no reasons to split it. And it stores nothing, just stores, I have nothing to declare. Quadrant 3 says I store D. It's a single point, I don't need to be split, but D has a lot of parameters. To start with, what is its exact X and Y? It can rise in various locations in the same quadrant. You need to store it with D. Maybe D has different parameters. If it's graphics, it has colors, it might have height, various other parameters. D stores all of them, and there is some pointer, or in the node itself, somewhere when you're visiting this node, you can get to all the data that associated with D. So we took care of 2 leaves by now. We took care of the southeast quadrant that only stores D. Similarly, for the northeast, that only stores A. Quadrant 1 has several points in it, more than one, so you need to further split it. You need to further split it until each quadrant over here, you have at most 1 quadrant. And along the way, you left a lot of empty leaves, by the way, but we'll show how many wasteful there is in this QuadTree. But you see that things with this QuadTree might be a bit strange, especially if you're used to other data structures, because I can take my QuadTree, put 2 points and that will be my input data. And to store them using this splitting policy, I'll have to create a pretty high tree. I'll have to split them until eventually, only the very last level, I can split it. So my quad tree will look like and only here. I can split them into A and B over here, where this node essentially has three null pointers, three empty leaves, and only one non-empty leaf. So if it annoys you, we will talk about a way to make the quad tree compressed, which essentially get rid of such long shreds by compressing them. And then we don't have such strange cases. Then the height will be log n at most. Right now, if I don't know anything about if the coordinates of these points are real, then I don't have any good bounds about how many splits do I have to do. But if there are real numbers, then all I know is that I need to keep splitting until now the height, the height without compression is log of the original size. How large was the original size? Divided by mean distance between points. That's how many times I need to split half until I finally succeeded to separate two very nearby points. But as we said, we have other tricks to do it, but at least hopefully everybody understands where this bound is coming from. You're starting from the side of the whole tree, split, 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 until you separated two very nearby points. Okay, let's see already why QuadTrees are so helpful in answering queries. Not about mesh generation, it's about reporting. I have a query region. Usually the query region will be a rectangle, but in the slides, it's easier for me to keep it as a circle, then you know what is a query region versus what is a square. And between the query region and R of V, the region that a node V corresponds to, there could be several options to the relationship between them. It could be that I'll have a query region, which means what? I want to build a Walmart right here in the middle. How many people live 5 miles away from me? I'm a player that just landed over here, but I cared only for other players that are 10 meters away from me. Who are the players that are in risk of hitting me, of collisions? It's a robot that moves among other robots that are all obstacles. And QuadTrees are really very practical in all these scenarios. So I have a query region, and I want to know, in this case, tell me all the points that place in it. A little variant that I'll ask you would be, tell me how many points there are that are even quicker. Here I want to know what the names of every point that lives inside the query region. So how do I perform a report? Q for this disk that is the query region, V is a node, R of V is a region that this node in the tree corresponds to. I have 2 minutes, that will be completely enough. I'm checking if V is a null by mistake. If yes, then there is no point. I don't care about the query, it's still a mistake. Otherwise, I'm checking if R of V for the node V is completely disjoint from the query region. Here is my query region, somewhere in the East Coast. Here is where I live in the West Coast. I'm completely disjoint. my city is, or the tree is completely disjoint, or for node V inside it, it's completely disjoint of the query disk. In this case, then of course there is nobody in the subtree that V corresponds to that is also inside the query region. So if our V is disjoint from Q, then we return null. The other easy case, if our V is fully inside Q, and V is, say, the root, or at least it has a subtree of itself, then obviously every point that lives in the subtree of V is also inside the query disk. So if you want to know how many they are, then maybe V knows already how many points there are underneath it. If you want to report all of them, then obviously if you visited the root or you visited a node and you realize that it's inside the query disk, then there are no more checks. Go to all the nodes in the subtree and report or count all of them. Now, if V is a leaf, that's an interesting case. If V is a leaf, V is a leaf like in this case, then it might be empty. There might be 1 point, few points in it. Check if they are actually inside the disk or not. I'm not sure about it. But I'm not in the case that the whole our V is inside the disk, so I need to be careful if the point inside or outside. Okay, almost done. The only interesting part is if our V partially overlap Q. The region of the tree or the region of the node is not fully inside, is not fully outside. Some points are inside, some points are outside. And then I'm saying it's none of my problems to decide which part is inside or not outside. I'll let my 4 children to decide for themselves to make these children. So I'm just calling myself recursively with each one of my 4 children with the same query. Just tell them about the query and let each one of them tell me who are the points that they correspond to that are also inside Q. And one of them might say, I'm completely disjoint from Q. Another one will say, I'm completely inside Q. Others will say, I have to recurse. So that's, of course, not in logarithmic time, depending on how many nodes I have to visit, but QuadTrees also comes with bounds about it's not catastrophically bad. Okay, thank you. Questions? Sorry about the OBS, I'm not sure what happened there.